So now that we've got some basic knowledge on kinetic and potential energy changes, we're going to look at this concept called calorimetry. And in this example, this is really just kinetic energy of one substance is affecting the kinetic energy of another substance. And the assumption that we're going to make is that all the energy that is lost from one substance is gained by the other substance. So the example I've got here on the board is I've got substance A is just say water, and we've got 100 grams of water and it's sitting at 22 degrees Celsius as its initial temperature. And we take a really hot block of iron, let's say 20 grams of iron, and we drop that block into the water. Naturally, we know what's going to happen. The temperature of the water is going to go up and the temperature of the iron block is going to go down to the point where they meet somewhere in the middle or meet at some common temperature, not necessarily at the middle, but meet at some common temperature and then just stay there and then cool, I guess, down together if you open that up to the environment. But what we're really assuming here with calorimetry is that this is a closed system. No extra heat is getting in, no extra heat is leaving, and so just the heat of the system is maintained, and so it's just really kind of like a perfect scenario where we have perfect insulation. And so if we do this, and this is what happens, we put the block of iron in, the 100 grams of water now is at 42 degrees Celsius, which is its final temperature. We've got the block of iron just sitting in the water at that same temperature as well. 62 degrees Celsius is kind of where they've met at. So what we can do is we can actually make a calculation with this. We can calculate, hey, how much water or how much energy was gained by the water when this happened. And so we can use our formula like we've done in previous videos, Q is equal to MC delta T, and plug in our numbers. Now the key here is that when we're calculating the heat gained by the water, you must use parameters of water. In these types of questions now, we've got two different masses. We've got the mass of water and the mass of iron. We've got some different temperatures. We've got some information here that we have to make sure that we're keeping consistent. So if I am calculating the heat of the water or the amount of heat that was absorbed by the water, I must use the mass of the water, the specific heat capacity of the water, and the temperature change of the water. And so you can see I plugged those numbers in. 100 grams of water, 4.19 joules per gram degree Celsius is the specific heat capacity of water. And then the temperature change was 20 degrees Celsius, a positive 20. When we went from 22 up to 42, that was an increase of 20 degrees. So I plug that into my calculator and I get this number, 8,380 joules. Now, based on this concept of heat lost equals heat gained, if this is how much heat was gained by the water, 8,380 joules, then we also know that that is how much heat was lost by the iron. Based on this, just this assumption that we're starting out with, this is our base assumption, that the heat gained by the water is going to equal the amount of heat that was lost by the iron block. And so you can see I've got the Q of iron is equal to the Q of water. Now just these negatives and positives are simply there to indicate, hey, this is heat gained and this is heat lost. And so if I gained 8,380 joules of energy for the water, that means that the iron block lost 8,380 joules of energy. And so for this, I can now use our formula of Q is equal to MC delta T, but this time for the iron. We know what the heat lost by the iron was. We just figured that out in this previous step. We know what the mass of iron is. It's right here at 20 grams. We know what the specific heat capacity is of iron at 0.449 joules per gram degree Celsius. That's found in your data booklet on page 3. And I've broken up the delta T into its components, temperature final minus temperature initial. And we know what the temperature final is. The temperature final for the iron block is 42 degrees Celsius. And so right here, we can plug that number in that formula. So the only parameter here that we don't have is the initial temperature of the iron block. And so that initial temperature is right here just prior to us putting it into the water. How hot was this block of iron actually? And so what I want you to do is I want you to try that problem out. See if you can solve for this algebraically. The answer right here is 975 degrees Celsius for you to be able to check your answer. So go ahead and give that a whirl and see if you can do that. And that's it for calorimetry, guys. We're going to do one more example that's a little bit different in terms of calorimetry, where we're incorporating potential energy and kinetic energy. So stick with me, I'll be right back in the next clip. So on to example 2 for calorimetry. And in this example, what we've got is we've got a chemical reaction that's occurring. And because it's a chemical reaction, we know that that's a change in potential energy. In the first example, it was one substance was really hot, had a high temperature, we put it into a cool substance, and their temperatures both changed. That was a change in kinetic energy to another change in kinetic energy. Here, we have a change of potential energy because it's a chemical reaction, and that heat that's lost in that chemical reaction is then being absorbed by another substance where its temperature is going to go up. So we have a change in potential energy affecting kinetic energy of another substance. Here we've got this fuel. In this example, it's methane, so CH4. It's just burning in a combustion reaction, and because it's a combustion reaction, it's an exothermic reaction that's going to release heat. That heat is going to go into, in this example, 2 different substances. We have an aluminum can here, as well as water that's inside the can. And so both the aluminum can and the water are going to gain heat. Now the assumption for this example is still the same as the first example, in that we have heat lost equals heat gained. But in this problem right here, this question is asking how many grams of methane is going to need to be burned in order to get these certain parameters. So here we've got 200 grams of water, 25 grams of aluminum, and the initial temperature of both the can and the water was 24 degrees Celsius, and the final temperature of both the water and the can was 92 degrees Celsius, based on this burning that took place underneath where that heat was going in. And again, remember too, we're assuming because heat lost equals heat gained, we're assuming that there is no heat that's lost to the environment. Naturally, there's going to be some of that, but we're assuming that amount of heat is zero. All of the heat that's lost by this fuel being burned is being absorbed by the can and the water. So that's why we can make this determination. So if I go ahead and I start to work this problem out, the Q of methane, so the heat lost by the methane, is going to equal the heat gained, but because there's 2 things gaining heat, some of the heat goes into the water, some of the heat goes into the aluminum can. So we have to add those 2 things together. So then I can calculate the Q of water and the Q of the aluminum. That's not iron, that's aluminum. And I can put the numbers in for those formulas. Now again, like I mentioned in the previous clip, you have to be really careful and vigilant that you're placing the correct numbers in the correct formula. So if I'm calculating the Q of water, then I need to use the mass of water, the specific heat capacity of water, and the temperature change of the water. And so you can see I've done that here. And then for right here, the Q of aluminum is calculated by using the mass and specific heat capacity and temperature changes of the aluminum can. So then I plug this into my calculator and I get this number, 58,508 joules, or in other words, 58.508 kilojoules. And then I can use my concept of potential energy calculations that we learned in a previous video to calculate how many moles of methane that then requires, and then use the molar mass of methane to calculate the mass of methane. Notice again that those parameters are consistent. Here's the heat lost by the methane. Here's the heat lost per mole of methane. And so then I can calculate how many moles of methane I have, and then I can use the molar mass of methane to calculate the mass of methane. So all of these numbers are related to methane, and so that's why we can use them in that way. And that's it. Our answer ends up being 1.17 grams of methane, which isn't a very large amount of methane in order to really heat up water in the can to a fairly high temperature. So it's a fairly effective fuel. And that's it. That's what you guys need to know about calorimetry. Thanks for watching.